Okay, minasan, konnichiwa, Zamurai Engineer desu. So in this video, we will tackle the different load combination pertaining to one of the method of or approach in designing steel elements and structures. So let's proceed. So specifically, we will talk about LRFD load combination. So we already discussed that there are two design approach. So LRFD and ASD. We are going to discuss first the LRFD load combinations. Again, let's start with the objective of the course. Our course will provide fundamental concepts, principles, and theories under structural analysis and design of steel elements in a structure. So we have the course outline. Currently, we are on the second major topic, and here right now we are on module number 8.2. So let's talk about first the symbols that we're going to use. So there are symbols or nomenclatures that we're going to use. So we have letter D for dead load, and that is usually in terms of pound force or kilopound force. Okay? That is for what? English units. So this is directly taken out from the IIEE standard code. So we can have our SI units equivalent for this when we have some of our problems. So there are different system of units. Okay. So D is dead load again. E, earthquake load. So earthquake load is one of the environmental load, as we already talked about. Again, same unit of measure, kilopounds or pound force. Okay. Letter F is load due to weight and pressure of fluids. When we are talking of fluids, so we will use F, the load, to represent weight and pressure of fluids. Take note. H we're going to use to represent pressure of soil. Okay. So there are two types here, fluids and solid. Okay. So fluid, those are gas and liquids. So letter F. And for soil, which is solid, we'll use H. And next one is L, live load. We will use L. It must be distinctly differentiated from LR, which is actually roof live load. So it's also a live load, but it is for roofing. Okay? Load from the roof. Okay, so next Q for service level force. Okay, so service level force meaning those are the type of loads that have to be expected during the operation, during the use of the structure. Okay, normal use of the structure. R, let us use that to represent rainwater. Okay, so for rainwater load, so we are going to use R. So we will not use S, that is for snow. We will use T to represent effect of temperature. In addition, shrinkage, creep, differential settlement, shrinkage compensating concrete, and so on. So as might again have to tell you, so these symbols are general in nature, meaning it could be used in timber design, reinforced concrete design, or steel design. Okay. Letter U, this is the required strength. Required strength. It is the one we need to design. Okay, so that is our requirement. So strength requirement. Okay, required strength. Okay, so when we are talking of the load, okay, with respect to the load, what is the required strength? Okay, that our structure must be able to withstand. So that is what we mean by U. W, the same with our previous technical knowledge on theory of structure. It is distributed load. W, capital, that is wind load. Okay, and since we have what distributed load, so we also have what concentrated load, which is usually represented by capital letter P. Okay. Another symbols, we have what load factor, and that is what. Next one is phi. So this is phi, not pi. So pi is different from phi. So phi represents strength reduction factor. Okay. So strength reduction factor has different values for what? Tension, for compression, for flexion, for torsion, and so on. Okay. So there are different values for that, and we must be able to memorize. So let us memorize or familiarize. So I think we need to memorize. Okay, because it will be used again and again, repeatedly. Okay. So let's go to the next slide. So let me check if there are questions. Okay, while so I think there's no question yet. Okay, so I'm checking. Okay, so there's no question yet. So just stay listening. So now we are going to discuss RIPdE. These are load combination that is only allowed by the code for RIPdE. We will see how many load combination, and you must be able to memorize this. Okay. So let's memorize this load combination for RIPdE. Number 1, U is equal to 1.4D. So meaning to say, so from our symbols, U is required strength, okay, and D is dead load. So therefore, required strength is equal to 1.4 times D. So 1.4 is the load factor. So as you can see here at the bottom, the second from the lowest, that is load factor. Okay, so the load factor is 1.4 if there is no other load other than dead load. So if only dead load is present, we have what? 1.4 as our load factor. Take note of that. Number 2, required strength, okay, is equal to 1.2 dead load plus 1.6 live load plus 0.5. Okay, so 0.5, this is LR. So this is what? LR. This is roof load, live load, or snow or rain. All of these has something to do with roofings. Okay? Rain will hit the roof. Snow will hit the roof. And LR, of course, live load for roofing. So what is the factor? 0.5. Take note, we do not need to use S. So when you memorize, just remove the S because it is for snow. In our country, there's no snow. So there are instances of hail, but hail is not snow. Hail is considered rainfall. Okay? Okay? So number 3, please memorize. Required strength is equal to 1.2 dead load plus 1.6 either roof load or rainfall load. Okay? Just remove S for snow load plus either live load or 0.5 wind load. Okay, so this is included in the third equation, live load or wind load. So we have live load and wind load. So meaning the load factor of live load here on equation number 3 is 1 and the factor for wind is 0.5. Take note. You have to memorize this equation with the name of the equation. What is the name of the equation? Equation 1. That is the name. Equation 2. So whenever I say equation 1, you should instantly be able to recall that 1.4 dead load is equal to U. Okay? So required strength is equal to 1.4 D. If I say equation number 2, required strength is equal to 1.2 D plus 1.6 L plus 0.5 LR or rain. Okay, so that's how you should be able to memorize this. So memorize this LR and D load combination. Okay, number 4, required strength is equal to 1.2 D plus, this is 1.0, this is not low, this is 1.0. Okay, so we can check this out. Let us check this out. That is number 4, that is 1.0. Okay, so I confirm that this is actually 1.0. Okay. Okay, so 1 times wind load plus what? Live load. Again, we would like to confirm what is number live load plus 0.2 snow load. Okay. So equation number 4. Let us confirm equation number 4. That is 0.5. 0.5 roof load, roof live load, or rain load. So this is correct, but there is what? An explanation. There is an asterisk. Okay? So the asterisk means, let us explain that the asterisk, the load factor in combination equation number 3, equation number 4, and equation number 5, okay, the factor of the live load is 1. Okay, this is 3, 4, and 5. Okay, and so equation 3. So here, so I already told you, I already explained that the factor is 1 here by the live load. So equation 4, the factor again is 1. And let's go to equation number 5. Next slide. Again, live load, the load factor is 1. That is what we mean by the asterisk. Okay? We have the explanation here. We have the explanation. The load factor on L combination 3, 4, and 5 is to be taken as 1. For floors in places of public assembly. Okay? For live loads in excess of 100 pounds per square foot, and for parking garage live load. So those are the conditions why we have this asterisk. Okay? So for other types of live loads other than the mentioned condition, we can put instead of 1, 0.5. 0.5 load factor. Okay? So that is what we mean by asterisk. Okay? Take note of this. Okay? And equation number 6, required strength is equal to 0.9 dead load plus 1.0 wind load. And equation number 7, required strength is equal to 0.9 dead load plus 1.0 earthquake load. So, how many load combinations? So there are 7 load combinations when we are talking of LRFD. Okay? So any question? So equation 4, 1.6 W. Okay, so that is 1. So there is no 1.6 for wind. Okay. So wind will always 1. So please memorize the 7 equations and memorize it properly according to the number of equation. So always the equation number 6 is 0.9D plus 1W. It is always like so. Memorize it that way. So let's explain further. So the following are several additional comments on the load combination. We are just talking of LRFD right here. Number 1, it is to be noted that in selecting design loads, adequate allowance must be made for impact conditions before the loads are substituted into combination expressions. So before anything must be substituted into equation 1 to 7, if you are thinking of an impact load, so you must make an allowance for that consideration. Okay? So number 2, load combination 6 and 7 are used to account for the possibilities of uplift. Okay, so what is equation number 6? That is with the use of wind, and number 7 with the combination of earthquake. So dead load and earthquake for number 7. Number 6 is dead load and wind load. Okay, and on this equation, possibilities uplift, meaning the load is going up. That is what we mean by uplift. The soil is going up during equation number 7, and the wind is going up during equation number 6. Right? So in consideration of dead load, which is going down, so wind is going up, dead load is going down. Similarly, for earthquake, that is the case. Okay? So therefore, it is possible that we may have what? Subtraction rather than addition. Okay? It will govern only such a condition. Okay, let's continue with the possibility of uplift. Such a condition is included to cover cases in which tension forces develop, okay, owing to overturning moments. So because when we have overturning moment, One side is compression, the other side is tension. It will govern only for tall buildings. So tall buildings where high lateral loads are present. So in these combinations, the dead loads are reduced by 10% to take into account situations where they may have been overestimated. So what do we mean by dead loads are reduced by 10%? So dead loads are to be multiplied by 0.9. That's why it is reduced by 10%. Okay? That's why it is multiplied by 0.9. Why? To account for situation, again, where they may have been overestimated. Okay? So, because we want to maximize the effect of wind and earthquake for tall buildings. Okay? Number 3, it is to be clearly noted that the wind and earthquake forces have signs that is, they may be compressive or they may be tensile. Okay? So that is tending to cause uplift. So tensile tending to cause uplift. Thus, the sign must be accounted for in substituting into the load combination. The plus-minus signs are not so much a matter of tension or compression as they are of saying that wind and earthquake loads can be in any horizontal and sometimes vertical direction. Okay, so let us now over here. Load combination 67 applies specifically to this case in which loads in a member due to wind or earthquake and gravity dead load counteract each other. I just explained this. Okay, I just explained this. There might be what? Opposite direction with the dead load. So for a particular column, the maximum tensile W or E force will, in all probability, be different from its maximum compressive force. So because of that, okay, take note of that concept. Number 4, the magnitudes of the loads, dead load, live load, roof load, and others should be obtained from the governing building code or from ASCE 7. So just like we mentioned, we have to use the recommended, the suggested values by the expert. Okay. Particularly when we do not have specific information of those things. Okay? So if you have measuring tools and you measure the wind load, the earthquake load, and then you can use your actual measurement and justify it for approval. Even though you have those measuring instruments, you still need to get approved by the building official. Okay? So wherever applicable, the live loads used for design should be the reduced values specified for large floor areas, multi-story buildings, and so on. Don't forget about this. Okay? And that's why I would suggest that you have to repeatedly review this video, rewatch this video, and repeat it every time there's confusion, okay? So that you might be guided by this concept. Okay? So let us take on example number 4. By the way, we will have this sample. We have an example number 2 which we may cover later. Okay, so we have yet to finish the example number 3. But that is from another book. So we are using this reference book. Okay, so let us consider the following sample. The exterior floor system shown in the figure has W24 by 55 sections. What do you mean by W24 55 sections? That is the actual name of the W-type structural element. 24 is the nominal dimension, and 55 means 55 pounds per feet. So 55 pounds per foot. Okay. So spaced how much? 8 feet on center. So meaning center to center. So 8 feet. So as you can see in the figure, so this is what? This is the beam which is on a shape of W type element with 24 nominal depth and 55 weight per foot. Take note, 4 feet on the one side and 4 feet on the other. So the total is 8 feet. Okay? So 8 feet on center. So this is the center of the span, center of the span. Okay? So this is the point of support. Point of support. So support to support, that is 8 feet. Also center to center of the span, that is 8 feet. Okay. Area of slab supported per foot of length. So this is the area, 1 foot. So per 1 foot, we have the area of slab. In what? In this strip. This is the strip, 1 foot. Area supported by 1 beam. So this is another beam. Okay. So maybe this beam is a joist beam. So this joist beam supports center to center slab. Okay. So let us continue with the problem, and the W24 by 55 section is supporting a floor with dead load of 50 PSF, so pound per square foot. Okay, 50 dead load, and a live floor load of 80 pounds per square foot. So 50 and 80. So therefore, the question is, determine the governing load in pound per feet that its beam must support. So let us determine, okay, how much in terms of pound per foot. Okay, we have an idea, pound per foot, no? So pound per foot is supposed to be computed. Okay, so let us compute all of the load combination. Let us take note of all of the load combination. So one by one. First, we need to compute for the major type of loads. There are only two, dead load and live load. Okay, so for each foot of the beam, okay, so for each of these per foot, okay, per foot of the slab, the dead load, okay, that is what? 55. Okay? Okay? 55 meaning that is the section, the W section. 55 pounds per foot. 55 pounds per feet. Plus how much? Plus 8 times 1 is equal to 8 feet of building floor. Okay, plus 8, okay, times 50. Okay, so 55, this 55 is self-weight of the beam, and 8 times 50 is the load. Okay, exterior load. So this is self-weight load, this is exterior. Okay, so 8 times 50, that is 400, plus 55, that is 455 pounds per foot. That is our dead load. Okay, are we clear about this? So we are just what? We are just computing per foot. So only this slab, we are just computing for this slab. So this slab is 8 by 1. So that is means 8. So 8 times 50. So that is 400 pounds per foot. And what about this 1 foot self-weight of the beam? So that is 55 pounds because the beam is 55 pounds per foot according to the name of the section. That is what? 24 by 55. So 55, that is the given, right? Take note. Okay, so meaning 455 again. Now let's go to the live load. What about the live load? So there is no self-live load, so therefore 80 is the floor load times 8, that is 640 pounds per feet. So we have the values for dead load and live load, and as you can notice, live load is a little bit greater than dead load. Okay, now let's continue with the formula. So there are seven formulas. So compute all the formulas. So number 1, that is what? 1.4 times dead load. Okay, substitute. So 1.4 times 455, that is 637 pounds per foot. Okay. Okay. And also recall all the formulas in theory of structure. Number 2 formula. Okay. So we use WU, small letter W, okay, because we are talking of uniform load. Okay, that's why we use W. Supposed to be we have to use U, okay, but instead we use WU. So question number 2, 1.2 dead load plus 1.6 live load, and we have 1,570 pounds per foot. Question number 3, 1.2 dead load plus 0.5 live load, therefore 866. Question number 4, so there is no rain load, there is no snow load, therefore question number 4, 1.2 dead load plus 0.5 times 640 again. So 3 and 4 will have the same answer because of there are only 2 given loads. Okay, same 866. Equation number 5, 1.2 dead load plus 0.5 640. Okay, 3, 4, 5, they are all the same. Why? So let us go back. Why? 3, 4, 5. So 3 and 4, take note. Dead load, they are the same. And live load, okay, is what? Here. Okay, so 0.5. Okay, 0.5. So here 0.5. Okay, so we have that And also, equation 5, 1.2 dead load. So, always 1.2. So, we do not have what? Snow load. So, therefore, that is, so for equation 3, 4, 5, the load factor is permitted to be equal to 0.5 for other types of live loads. Okay? So, because we can use 1 for places of public assembly. We do not know if the example is for public assembly. So, we can use 0.5. Okay? For live loads in excess of 100. So, the live load is not in excess of 100 because it is only 80. It is only 80. That's why we can use 0.5. Okay? And that is not for parking. So, therefore, we can use this portion, 0.5. So, we have to use 0.5 for other type of live loads. That's why we use that value, 0.5. Okay? So, that's why equation 3, 4, and 5 are the same, 0.5 times 640. Okay? So, take a look. So, 640 is our live load. Okay? So, that's why 0.5 times live load. So, they are all the same for equation 3, 4, and 5. What about equation 6? With the wind load, there is none. So, only dead load. So, 0.9 times 4, 5. What about earthquake load? Equation 7, there is none. So, only 0.9 times 455 dead load. So, these are the values. So, after computing the 7 equation, what we need to do is compare. Compare this value, 637, 1570, 866, 866, 866, 409.5, 409.5. Which one has the highest result? The highest result is 1570. That's why we need to use 1570 pounds to be our design required strength. Okay? So that is our answer. Our answer is 1570. There is one answer to this, but there are plenty of computations. Take note, there are plenty of computation, although we only have one answer. Okay? Take note. Okay? Okay, there are no questions. I am looking at our comment box. No question. Let us go to example number 5. A roof system with W16 by 40. Okay, another W type. Okay, 16 is the nominal dimension, 40 is the weight. So 40 pounds per foot. What is the spacing? 9 feet. On center is to be used to support a dead load of 40 psi, a roof live load. Now, we have a roof live load. Unlike on example 4, we have a live load. Okay, now we have a roof live load and snow or rain load of 30 PSF. Okay, PSF. Roof live load, snow or rain load, 30. And a wind load of plus minus 32 PSF. Take note, we have plus or minus. Okay? Okay, compute the governing factored load per linear foot. So, solution, again, let's start with dead load computation. That is equal to what? The dead load of the dead load on the element is 40. Okay, that is self self-weight plus 9. 9 is the spacing. So 9 times what? 40. That is what? 360. So 360 plus 40, that is 400. So how much is the live load? 0. How much is the roof live load? 270, because we have 9 center to center plus 30 times 30, that is 9 times 30, 270 for rain load. Now, what about wind load? Wind load is 32. So 32 times 9. Okay? So the wind will hit all of the element, the 9 on center. Okay? So this is a roofing. So the wind will hit the roof. Okay? So 9 feet of roofing. Okay? So times 32. So that is 288, and that is supposed to be plus minus 288. Okay? Take note of that, because we will use that value in two ways. We will use it in plus, we will use it in minus. Okay? Because there is a possibility for the wind to go right here and to go on opposite direction. So going here in opposite direction, that is plus or minus. Okay? So let us proceed to the 7. Let us proceed to the 7 equation. Okay? So number 1 equation, dead load times 400. So that is immediately 560. Equation number 2, 1.2 times 400 plus 0.5 times 270. 0.5 because we are just using rain load. Okay? Okay? There is no live load. So this is 615. Okay? And number 3, 1.2 times dead load plus 1.6 times 270. Okay. So 270 is what? Take note. Take note on the So roof live load. Roof live is no or rain load, or the word or. Okay, it could be roof live, could be snow, it could be rain. That is 30. So 30 times 9, that is 270. So 270 could be LR, S, or R. Okay. So what about the equation number 2? So equation number 2 is what? What number equation number? Equation number, now on the equation number 3. So equation number 3. So we have live load, we have wind load. Live load and wind load. So equation number 3, that is 1.2 D plus 1.6 LR, okay, plus 0.5 W. So plus 0.5 W is 288 times 0.5. So that is 1056. Okay? Note. So the difference with that, with the equation number 2. Look onto your copy of equation number 2. Equation number 2 is 1.2D plus 0.5 LR, S, or R. Okay? That is what we mean by this. Okay? Okay? So, however, on the equation 3, 1.6 is multiplied by roof live load. Okay? So, that is a difference between equation 2 and 3. Right? And equation number 4, 1.2 dead load plus 1 times wind load plus 0.5 roof live load. Okay? So, that is equal to 903. Okay. Now, number 5, equation number 5, 1.2, the dead load plus 0.2, group live load is equal to 534 pounds per foot. And number 6, we have the equation for wind. So, number 6, equation for wind. That is 0.9 dead load plus 1 times positive 288. And the other one, letter B, is 0.9 times dead load plus 1 times negative 288. So if you use negative, it will become 72. If you use positive, it will become 648. So we don't need to compute, or if you will, you can compute number 7, but equation number 7 will give us the same as equation number 1 because there's no earthquake load. Only what? 0.9. Not equal to equation number 1. That is 0.9 times dead load. Okay. And since we have 0.9 times dead load, please compute 0.9 times dead load. So we need to include it here, 0.9 times dead load. So equation 7 here. So we have what? So we will copy it. Copy. So 7, that means this is 0.9. So please compute what is 0.9 times 400. That is 360. Is this 360? So 360 pound per foot. So according to Josh. Okay, so therefore, after that, we can now what? Compare all the results. Which one has the highest value? The highest value is equation number 3. So therefore, our answer is 1,056 pounds per foot. So that's how we compute the load combination. Okay. So we will now use 1,056 pounds per foot for our design. Okay. That is the load of our structure. Okay. So next example. So we have sample number 6. The various axial loads for a building column have been computed according to the applicable building code with the following results. Okay. Dead load 200K. Okay. Load from roof meaning 50K, so roof live load. Live load from floors reduced as applicable for large floor area and multi-story column. So we already reduced. That is equal to 250K. We can only reduce that if we have what? Large floor area. Okay. So compression wind is equal to 128 K. And then tensile wind is equal to 104 K. So what do we mean by this? Compression wind, tensile wind. So instead of having plus or minus, there is one value for compression and another value for tension. Okay. So next, compression earthquake 60K and tensile earthquake 70K. So the question is to find out the critical design column load, PU, capital PU. So we want to find out the what? The concentrated load. Okay, using the LRFD load combination. So let's do it. So wind, earthquake, live load, roof live loads, and dead load. So we have 4. So let's have a solution. This problem solving solution assumes the column floor live load meets the exemption for the use of the load factor of 0.5. Okay, for equation 3, 4, and 5. Okay, so for live load combination. Okay, so 3, 4, and 5. So there is a one condition. So if it meets the condition, okay, so what is the value of roof live load? Given roof live load is 50. So that is 50. We can use for equation 3, 4, and 5. What? The following. Okay, so equation number 1, 1.4 times dead load, easily 280K. 280K meaning kilopounds. Okay, that is what we mean by K here because we are using English units, kilopounds. Okay, so concentrated load, that's why we are using capital P. So previous example we use W, small letter W, because we are solving uniform load. Okay, so now concentrated load. So equation number 2, 1.2 dead load plus 1.6 live load, then 0.5 roof live load. Okay, so equal to 665. Okay, so equation number 3, A. Okay, so there are 2 for equation number 3, A and B. So letter A, 1.2 times dead load plus 1.6 times group live load, okay, plus 0.5 times live load, okay. Okay, so that's how that become 445. Okay. What about letter B? 1.2 dead load plus 1.6 roof live load plus 0.5 is equal to 128. Take note. So 250. So let us recall that is either rain or live load. Okay. Okay. So 128 is wind. Okay. So 128 and 104 are wind, 60 and 70 are earthquake. Okay. So we have 1, 2, 3, 4, 5 different loads. Dead load, roof live load, wind load. There are 2, so 5, and earthquake load there are 2, so 7. There are 7 values. There are 7 given values. Therefore, let us find out. We are now on equation number 4. is equal to, take a look at your equation, number 4, 1.2 times dead load plus 1.0 times 128. Okay, so again, what is 128? That is, I think, wind. 128 is wind, so compression wind. Okay, so that is for equation 4. So that is equation 4. That is wind times 1. Okay, so 1 times 128. And then also, if we use the negative 104, also multiply by 1. And because of that, for number 4, we have 518 and 286. We have lower value 286 because we use the negative value for tensile, no? Tensile wind. Okay, that is the common convention in the design subject. Tensile, negative. Compression, this. Okay. So we have anyway, you can create a combination that would make our answer maximum. That is the purpose. So we should have combination of load from our formula using our given values. So if you use negative 128 and positive 104, both of these values would become what? Lower than it is now. We need 128, which is a bigger value, to be positive so that it would become bigger. The result will be bigger. That's how you intend. Always do this. Always do this in this load combination solution in problem solving. The target, the concept is make the result bigger, higher. Okay? So do not be confused, okay, by positive or negative. Okay? So equation number 5. So again, we have what? Positive, negative. Okay. So 60 compressive, earthquake, 70 tensile. Okay. So as you can see, 70 is tensile. Okay. Tensile earthquake, 70. Okay. So next, equation number 6. So that is for wind. So only use the values for wind. So plus and minus values for wind. And equation number 7, use the plus and minus values for earthquake. So that's all. So there are 7 equations, but look how many equations we actually computed. So there are 8 and what? 8 and 12. So there are 12 computation of load combination. And let us compare which result is the highest. So which result is the highest? 665. Equation number 2. Equation number 2 is the highest. So therefore our answer is equation number 2, 665. So it will be noted that the result of combination 6A and 6B do not indicate an uplift problem. So, okay. Result. The result of this 6A and 6B. Okay. Okay. Uplift problem, meaning if here, uplift problem should be here. So, if the value of negative is higher than the positive, that is the uplift. Okay? There are times when that would become true. For example, in typhoon, during typhoon. Okay? So, the typhoon wind load is so large so that the resulting value here would be negative. That is an uplift. Uplift. Okay? Similar is true with earthquake. So if there is a uplift, the result would be negative. That is what we mean by this explanation. So next is our last slide for your challenge question. This is a material engineer problem. Number 10, what is the ratio of mortar used for stone masonry? Portland cement is to sand. So that is what we mean by mortar. So the mixture of Portland cement and sand. So letter A, 1 is to 1, B, 1 is to 2, C, 1 is to 3, D, 1.5 is to 2. So for example, in letter C, 1 is to 3, meaning 1 part of Portland cement for every 3 parts of sand. That is what we mean by these choices. Okay. Again, there is no question. This is your professor, Dr. AP, Teaching Engineering for Nation Building.